Take us back to page 6, where we talked about some logical equivalence situations. And I said that we would skip over this, so we skipped over it last time. But I think there's some value in doing it, especially since the assignment that I'm going to give you later on involves you making truth tables, logic truth tables. So, among other things. So it's worth taking the time to review a little bit. So the first one it's kind of unfortunate. I get the ordering here; they're not consistent with the actual examples. So the first one is actually the inverse. So that corresponds with this one here. All right. So what we're going to see is that there are some circumstances involving conditionals that bear themselves out to be always true, sometimes true, and never true. Right? So we're going to focus on the always true and the sometimes true. Right? So in the case of an inverse, that's when you take the original conditional and just negate each part. Right? So premise, conclusion, P, Q becomes not P, not Q. Right? And what this is going to show us is whether or not these two expressions are equivalent to one another. That's what the double-sided arrow represents. All right, equivalence, logical equivalence. All right, so our breakdown for P's and Q's for a two-variable set would be they could either both be true. Maybe the first one's true and the second one's false. First one's false, second one's true, or maybe they're both false. All right. So the idea here is that we cover the full spectrum of truths and falses, every possible way that a sentence containing a premise and a conclusion can be true or false. All right. I have to say I'm not really 100% sure what I was thinking when I made the not Q come first. It's fine, but it really should be the other way around. So I'm just going to make that adjustment here. This one should really be not P, and that one should be not Q. That's I call that a legacy typo. It's every single semester, and whether it's this course or another course, I use the same notes for logic, and or at least in the beginning. I always mean to make the change, but I always forget. So there you go. So not P is going to be the opposite of all the P values. So false, false, true, true. All right, so I'm just taking each one of these truth values and reversing them. All right, so instead of true, it becomes false. Same thing with the Q's. Instead of true, it becomes false. False becomes true. So I'm looking at this column here. I'm taking the reverse truth value of each part. All right, so now I have all my ingredients in order to tackle the rest of it. So the P implies Q is going to work off of the original set. Let me turn my fill color back on. I'm going to go with a nice light green for those keeping score at home. So I'm looking at this set here. All right, so those, that's weird. I'll just do it this way then. Oh, because I left the geometry tool on. So I'm looking at those two, I'm comparing them to determine the truth value of P implies Q. All right, now just a refresher. So, and honestly, a course that meets once a week, it's probably a good idea to do a refresher. So for a conditional, true implies false is false, otherwise true. All right, so this is a rule for conditionals. True implies false is false. Every other instance is going to give us a true. So I look across the board here, I see true and true. I see a true and false, false and true, false and false. The only one that's going to give me a false would be the true then false. Everything else is going to be true. All right. Then we're going to look at the not P and the not Q. And that's going to give us our next column, applying the same rule. True implies false is false, otherwise true. So I go across the board here, I see false and false, false, true. This is the one that'll actually be false, true then false, true then true. All right. So the only instance in which we're going to get a false is this one. Otherwise, it's going to be true. The biconditional, I think, is actually the easy one. Right? It's easy for me to say, I know. But the biconditional is true if the truth statements are equivalent to one another. Right? So for a biconditional, true, double-sided arrow, true, false, double-sided arrow, false, is equal to true. So we kind of think, I think we talked about this last time, we kind of think of that double-sided arrow as an equal sign. So we look at the two components and say, are they the same? Yes, then it's a true sentence. Are they not the same? Then it's going to be a false sentence. All right. So let me get like an orange here, or whatever color that is. Just verifying that it's actually somewhat visible on the big screen. So comparing these two together, just looking for any instance where it's true, if and only if true, you say if and only if for the double-sided arrow, or false if and only if false. So we have a true. These two are the same, so it's true. These two and these two are different, so false. These two are the same, so true. All right. So what we get from this, because we talked about, we did it very briefly, admittedly. We talked about whether a sentence was, or it could be a compound sentence or a simple statement, is true. Is it valid? Is it satisfiable? Or is it unsatisfiable? Valid means that this last column is all containing true values. Satisfiable means there are some circumstances where you would get a true result, but not all of them. Unsatisfiable means you got false all the way down this line. All right. So we can now conclude for an inverse we have the P implies Q is going to be the same as not P implies not Q only when P and Q are both true, or P and Q are both false. Right? And the reason I can say that is just going back to our original statements of truth here. The only instances in which we ended up with a true outcome here and here corresponded with true, true, false, false. All right. So, I don't want to go back to the shoes and socks examples, but, kind of, it's the bread and butter. It makes it, easier. So if I say, if I'm wearing shoes, then I'm wearing socks, that would be equivalent to if I am not wearing shoes, then I am not wearing socks, only if it's true that I'm wearing shoes, true that I'm wearing socks, or false that I'm wearing shoes, false that I'm wearing socks. Right? That's a lot. The satisfiable instances are kind of weird, but when we get to probability, you see how it all kind of comes together. Right? It allows us to disregard instances that are not possible. All right, so that's I'll make a note of that. This is satisfiable. I don't know why I just put quotes around it. I just did. The next instance is the converse. All right, so same initial structure. True and true, true and false, false and true, false and false. We look at the first two columns here, these two, and this is going to help us figure out both the third column and the fourth column. All right. So again, the only time a conditional sentence is false is if the premise is true and the conclusion is false. So true, false, true, true. Now the Q implies P is a little weird because it means that we have to read it backwards. All right. So when I'm looking at the P implies Q here, I'm looking from P to Q. All right. So the P column, then the Q column. For Q implies P, I'm still using the same information. I'm just reading it the other way around. All right. So here I'm looking at this as the premise, this as the conclusion. Premise, conclusion, and so on down the line. All right. So reading it in that fashion, and I'll actually do it. So we're reading it backwards. We'd have true then true, which is true. False then true. So the second row here, false then true. That's going to be true because again, it's not this one instance where you'd have a false outcome. The third one, true then false. That's the only instance in which it'll be false. False then false for the last one. Result is true. All right. And again, when we look at the biconditional, so now I'm comparing these two columns. When I look at the biconditional, I'm just looking to see if the truth statements are the same. If they're the same, we say true. If they're opposite of one another, then we say false. So we have true, false, false, true. All right. So we actually have the same satisfiable circumstances here. All right. For the converse, which is P then Q, looking for instances in which it would be equivalent to Q then P, parentheses or no parentheses, it's up to you. Only when, so I'm actually going to write the same stuff here. So only when the P and Q values are both true or the P and Q values are both false. All right, so I'll just chuck that right there, I guess. But then we have the contrapositive. Now, if you looked ahead to the next page, you'd see there's actually a law of contrapositives. So this has got to be a pretty important one. All right, so it's the same setup. I've never made a worksheet I couldn't make a typo on. I don't know why I have 5 rows here. There's no reason for that. I'll just X that last one out. All right, so same setup. True, 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 false, false, true, false, false. It's just one of those sheets where I guess I couldn't get out of my own way. There's like so much wrong with what I have written here. Yeah, there should be P implies Q. Oh, this is brutal. Why did that crash? Maybe it's my my technology just giving up. It's being like, dude, you have too many mistakes on this. It's time to just call it. Nah, we'll fix it. So it should be. I don't even know how to salvage this. You know what I'm going to do? I'm just going to draw a new table here because it's really that bad. All right, so I'll just do it here. I don't need the shading. So I swear I revise my notes in the beginning of every semester. I guess if I miss it the first time, it's like proofreading your own papers. Like if you made the mistake to begin with, you're probably not going to pick up on it. All right, so P, then Q. So again, true, 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 false, false, true, false, false. All right, so now I want another column for a not P and a column for not Q. I mean, the one byproduct of this is, I mean, the table's not always going to be made for you, so at least I can show you how you're supposed to construct it. You look at the ingredients of what you're trying to prove, and so ultimately, I mean, aside from this nonsense here, what we're trying to prove is that P implies Q is logically equivalent to not Q implies not P. So that's what we're going for. All right, the not Q implies not P. That's the contrapositive. All right, so it's a combo platter of the converse and the inverse. All right, so I just look at, whenever I'm creating a truth table from scratch, I look at all the ingredients that make up each part. So I have a P, a Q, a not P, and a not Q, and you can put it in whatever order you want. I'm going to put the not Q first, because ultimately we're going to have to look at this. So I want to have it as ready to rock and roll as possible. All right. Then we're going to have a column for P, then Q. Then a column for not Q, then not P. And then a column where I somehow smush in everything that's written right here. So I got to write small. All right, so I know it's hard to see, but what I wrote up here is what is down in here. All right. So I find not Q, which is the opposite of all the Q values here. So I'll do that in blue. So false, true, false, true. The not P column is the opposite of everything that's in the P column. So false, false, true, true. All right, so then P, then Q. I'm going to use this, kind of make it nice, or as nice as I can for a handwritten jammy here. So this one, we're looking at true, 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 false, true, true. All right. It's the kind of thing where you do the same thing enough times, it's like, all right, well, now I just know it's TFTT. Why? Because it's always that. All right. The next one, we're going to look at not Q, then not P. All right. So false, true, false, true, true. All right, because again, the only instance in which you're going to end up with a false sentence is if the first part is true and the second part is false. All right. So the biconditional is the instances in which the truth values are the same. All right, so I have true, true, false, false, true, true, false, false. It's the same across the board here. So true right on down the line. So this is what we call valid. All right, every circumstance leads to a true outcome. Right? So no matter what the arrangement is of trues and falses in the P's and Q's to get started, the outcome is always going to be true. Right? Also known as a tautology, but valid is a much shorter word. So we go with that. Now, we want to get to a point, maybe not this semester, but if you're interested in logic, I know I've given enough analogies about, the law school admission test, the logical reasoning part, although I never remember what classes I make those analogies in, but there's a hefty logical reasoning component on there. Yeah, like you don't have to memorize the entire list of logic laws on the next page, but you should have some familiarity with the important ones, right? Because it does make life easier. In this class, specifically for probability, but in terms of just decrypting what somebody might have written in the form of a contract, you avoid loopholes if you end up with, like if you have a contract where, just going back to the converse and inverse stuff, if you have a contract where the premise has been met but the conclusion hasn't, then what happens there, right? Like what's the outcome? It's really more for the case where the premise has not been met. Then it's like, well, what do we do? Because those lead to true statements. So if I say, I just go back to the one of the examples I gave very early on, which is if you get a 90 or above, then you get an A in the class. And then I followed that with saying, well, what if you get an 85? So you didn't get the 90 or above. I can still give you the A for the class, or maybe I don't. Either way, I'm fine. I like that conditional is irrelevant at that point, right? Because I can do whatever I want because you didn't meet the condition of getting 90 or above, all right? So it's the same thing with like a contract for a phone or insurance policy, mortgage. Like you signed a contract to say that I'm going to make payments on a monthly basis, and they'll say, okay, if you make payments on a monthly basis on time, then you get to keep your house, right? So I didn't make my payments on time. They can do whatever they want, right? Because I didn't meet the condition. So they're not obligated to let me keep the house. Maybe they'll be nice and let me keep the house, right? Maybe they'll work out a payment plan with me, or maybe they'll just come and foreclose, right? So that's the power of the conditional sentence, right? At least in an everyday sense, right? So we have laws of logic. The laws of double negation, that was the one I told you that there was a little edit there. It should have been not P. Right? It's basically negating a negative. So two negatives make a positive. Yeah.
What's the rule for a tautology?
The rule is that it doesn't matter. It's always going to be true. All right, De Morgan's laws we touched on when we were doing Venn diagrams. It's a nice way of simplifying a complicated expression. All right, so if you have a negation involving an and or an or, not only do you negate the two statements that make up the and or the or. Let me do a highlighter there. So I have too thick. Highlighter's too thick. Undo. All right, so I would negate the P. I would negate the Q, but I would also negate, quote unquote, negate the connector. All right, we consider ands and ors to be opposites of one another. All right, so we'd basically flip the sign. All right, and that's the same case for the other way around. If you started off with an and, then it would become an or. Commutative laws are important. Associative laws, you'll see them from time to time, but I'll put stars on the ones that we're going to focus on the most, or asterisk. So De Morgan's laws, commutative law. I put a star on number 8 just because I think that's a funny word, but it doesn't really come up very often. Idempotent. It's like it looks for everything like it's not a real word, but it's a word associated with logic. Absorption laws, syllogisms, disjunctive inference. Well, it might be easier for me to star the ones we're not going to use. All right, so basically all the way down the line from here. Not a requirement that you memorize it, right? So, if I went the test route for this unit, I would give you these laws, all right? So you'd have access to them. It'd be like right on the I'll give you like a formula sheet. It's more important that you're able to look through them and see what's relevant in a particular situation, all right? So that's what we're going to kind of work towards. All right, so I'm going to do a couple of logic proofs here. The idea is that we can kind of, I'll say, graduate away from using truth tables. It's really more like, hey, the truth tables are going to work. I just don't want to spend the rest of my life using a truth table to try to prove something that I could prove using a law. All right, so that's the rationale here. It's not to take something and make it more complicated. It's actually designed to simplify. These laws of logic help you simplify expressions and make them less complicated. All right, so that's the plan. This one I knew in advance that I made some mistakes on, because the second example on your paper is exactly the same as the first example. So that's not good. So I changed the second one. We'll get to that in a minute. I don't know why I have this arrow here. It's not relevant. So we're going to look at the first one. And again, it's justify each step in the following proof. So on the left-hand side, we have all the different conclusions that we can draw from these three premises. All right. So this is a premise. So premise, you might have, if you're familiar with proofs, it's given information. All right. So all three of these things are given. It's not like you would be expected to come up with your own problem. I give you the problem and you solve it. The first three pieces of information are given pieces of information that you would use in order to prove the remaining stuff. All right. So it can be a little complicated, but if we use the laws of logic appropriately, then things will work themselves out. All right. So now this is our first foray into using laws. So it's understandable that it's not, oh, I would have never thought to do that. Well, yeah, because this is the first time we're seeing it, right? But the more I show you, the more obvious it'll become, all right? So the first thing that I'm going to look at is this conclusion here somehow comes from all of this stuff, all right? Now let me show you how that happens. So if we take the second premise, which is S or L, and make that look more like an or, then not G, and pair that up with S or L, we can draw a conclusion from that. All right? It's just not obvious based on what we've covered so far, but it is something that we could do. All right. So I'm going to put a little underline there. I'm going to pull the relevant rule and just show you the relationship. All right. So number 17 is modus ponens. It's also called the law of detachment, which might feel a little bit more on point when it comes to what it's actually doing. But I'll show you the ingredients that make it up. What this is saying is P implies Q and P is logically equivalent to Q. All right. Written another way, so we could write it kind of like the way I wrote it down here. I could write this as P, then Q, and P. It's a little shorthand way. If you put two pieces of information together, in this case a logic sentence and a logic statement, it's implied that there's an and there. So it's this and this. The result, three dots in the form of a triangle, means therefore, or the result is Q. All right. So the modus ponens actually, it stands for affirms by affirming. All right, which it's basically, I kind of look at it like, you know, the everyday language. If I'm wearing shoes, then I'm wearing socks. And then I follow that up with, I am wearing shoes. What would you say? If I'm wearing shoes, then I'm wearing socks. I'm wearing shoes. Then I'm wearing socks. Right? Because it's confirming the premise. Right? If I get a 90 or above, then I get an A for the course. I got a 90 or above. The logical assumption would be that you get an A for the course. Right? Now, the one that we have, or the pairing that we have here, is a little bit more complicated, but it has the same structure. We have an if. Here's my if. We have a then. Just like in the P and Q, we have an if and we have a then. All right? The if is being confirmed. All right? We have a matching if. We have a matching if in this case too. So we can conclude that not G is going to be true. And the reason, and by the way, I mean, we already knew that because it says it in line 4, but we didn't know why. All right, so now we know why. It's called modus ponens. And you could actually use the rule more than once. I mean, a logical sentence is just, I mean, it could be everyday language, but it could also be purposefully convoluted. So more complicated than it needs to be. And so what we can do is take that complicated sentence and try to simplify it. All right, that's really what's happening here. So I'll show you. If we look at the not G and now apply that to that first statement there, we're looking at really the same thing. We have not G, then bracket G or, and my or game's a little off here, or S then G. All right, so that's our first sentence. But if I couple that with a not G, it's the same concept. It's just it's not very pretty. Right? It's not quite as nice as P then Q and P gives you a Q. That's nice and simple. That's the shoes and socks. Here it's not this, if not this, then this or that, then that. You know, like, without a sentence, it's not, you have no hope to be able to reason through it without the laws of logic. All right? But if we confirm the premise, my if, has been confirmed, then the result has to be whatever the conclusion is. G or S then G.
How do you know which law to use?
Well, that's the thing. and we're taking baby steps here. So we're starting off really learning about modus ponens, but the idea is if you have an if then sentence. So here's my if, here's my then. What I'm looking for is any statement that confirms the initial part of it. All right. So whatever comes before the arrow, I'm looking for that somewhere else in my list. If I can find it, then I can use that along with modus ponens to figure out this other piece.
So it's always modus ponens?
Not always. We're going to learn about another one in a second. And then we'll be able to kind of piece it together and see under what circumstances you use one or the other. All right. So far, it's been modus ponens, but it's going to change in a second.
Because I don't know if you explained it, because I was a little late. Where is the 3 not?
Therefore. Yeah. All right. So modus ponens would be the rule for the next one. And again, you want to develop some familiarity with the rules, but it's kind of hard to know what rule to use without experiencing it at least one time, right? So looking at the next one, and you think about what we've used so far, right? We've used the first and the fourth statement here. We've used the second and the third. So now I'm looking to see if I can combine the statements in other ways. All right. So I use 2 against 3 with modus ponens to draw a conclusion, but maybe I could have used 2 against something else. All right. So that, it's not the easiest thing in the world, but it is possible that you can go back and use a rule that you've already used just in a different way, right? But what the problems that I designed them so that you would always use an additional rule down the line, right? So, like for example, we just drew the conclusion that this is a true sentence, right? That was by modus ponens. Now I can use that. I know it's a fact. I can use that along with one of these other pieces here and see if I can simplify it further. All right. So that brings us to another important law, which is called the law of disjunctive inference. I'm just going to move this a little bit. All right, so the law of disjunctive inference is what we're going to look at now. It's a law that allows you to break up a disjunction. So you could break up an or sentence. So let me pull the law. If we have P or Q and not P, the result is going to be Q. But there's another variant of this. All right? P or Q and not Q will give us a result of P. All right. So those are the laws as they're written up here. What I want to do is I want to see how that ties together with the example that we're working on here. All right. Yeah. So I now have a G or S then G. All right. So G or S then G. I also have a not G here. So this follows the model that we have. I'll box in the right one. This model right here, where we're looking at an or sentence, and the first part of that or sentence is refuted. Right? So if I tell you I'm wearing shoes or socks, and then I immediately follow that up by saying I'm not wearing shoes. Well, if it's shoes or socks and I'm not wearing shoes, then it has to be socks. All right? So that's what's happening here. P or Q. Well, it's not P, so it must be Q. All right? The more complicated sentence G or something else. Well, it's not G, so it must be the something else. And so that ends up being the statement that we would use for number 6, S then G, but we get that by the law of disjunctive inference. All right. In the end, I can tell you this, it's not going to be as important that you know the names of the laws. You just have to have some familiarity with the laws themselves. Like when I say it's P or Q, well, it's not P, then you should say that the result has to be Q. If I say it's my left hand or my right hand, well, it's not my right hand, then it has to be my left hand. All right? Whether that's called the law of pickles or the law of disjunctive inference, it doesn't make a difference as long as you understand the underlying concept. All right. So then we have a not S somehow comes from all this. So another law is, well, actually we can use, yeah, no, we have to, I was hoping that we could use one of the laws we had already a second time, but it's not, unfortunately, in the cards. Right? So another law is called modus tollens. All right, that's denies by denying. All right, and I'll show you what that looks like. All right, the rule itself is P then Q, not Q. The result would be not P. All right, the everyday language of that one would be if you get a 90 or above, then you get an A in the class. So if you get a 90 or above, you get an A in the class. I'm saying you didn't get an A in the class. So the natural conclusion would be, well, I didn't get a 90 or above then. All right, so it's just kind of following the process associated with the rule itself, but kind of tying it to the everyday language. I think that makes all the difference. Right? It takes something that's really weird and makes it less so. Now, in this case, I'm looking at, I have two pieces of information that I could use to draw the conclusion of not S. So I have an S then G, which we just came up with from the previous step. And I also have a not G floating around in there. As a rule, we want to use the simple sentences or simple statements to bust up the more complicated ones. All right? So I'm gonna use that not G for all it's worth in the hopes that it'll help me simplify things further. All right? Now, if I'm following this, you see here, Q, not Q, G, not G. All right? It's the same structure. So if my result for modus tollens, knowing that the conclusion was refuted, P then Q, so I said it's not Q, that means that we're looking at not P. By the same reasoning, S would become not S. All right, so that's a modus tollens situation. And finally, we could use one of the laws that we already have on the books here a second time. We use modus ponens twice. So we'll be able to use law of disjunctive inference a second time here because in order to get an L out of this, out of all of this mess here, really the only way I can do it is by combining this S or L here with the not S. All right, so that's again saying if I have this or that, well, it's not this, then it must be that. And again, whether you want to use the name or not, it doesn't make a difference as long as you can get that conclusion. Now, I'm giving you, like in these proofs here, I wanted to give something with a little structure to get started. But ultimately, as long as you can do the simplification process, the laws aren't as important. I just wanted you to be able to go back into that list of laws and say, oh, that's why I was able to make that conclusion. Right? So this is law of disjunctive inference. All right, so now that we've done one of the trickiest concepts that you'll ever see in your life, let's do another one. All right, this is the one that I had to write separately. This one is actually a little less complicated. Well, I guess everything's a little easier the second time around, but also I kind of stacked the different components so that it's easier to kind of group together. All right, so let me just clean up this a little bit. I'm just going to put this over here. Oop. I'll resize it a little bit. So all of this was for this example here. My little bracket there doesn't look so good. Okay, yeah, so it's a lot, but the whole idea is that we learn about the laws and then we can apply them, and it'll get easier as we go. All right. So for the next example, we have right off the bat P then Q along with a P. All right. By modus ponens, that's the affirms by affirming. If you get a 90 or above, then you get an A. Well, you got a 90 or above, so I get the A. All right, so that's going to give me this Q as a conclusion here, the one in step 5. All right, so that's modus ponens. That's the justification for that one. What I like to do, and admittedly the previous example is a little bit more complicated, but what I like to do is once I draw a conclusion, hunt around and see if I can find another expression that has that letter in it. All right, from starting with the premises and then going to the stuff that we conclude along the way. All right, so the only other expression that I see that has a Q in it is the R or not Q. All right, so I'm just going to do that off on the side. R or not Q along with a Q. So another application of disjunctive inference, which is what this is the concept of canceling. All right, if I tell you that you are going to wash the dishes or you are not going out tonight. Right? You're going to wash the dishes or you're not going out tonight. And then I say, well, you can go out tonight. The reasonable conclusion is that you must have washed the dishes. Right? So we kind of look at these as canceling one another out. And I could show you again up here. That's really what happened. We had two opposite components. One contradicted the other, so the remaining part of the or must have been true. Right? So that's what's happening here. These two things contradict each other, so they negate or cancel each other out and leave you with just an R. All right? An or, and we're going to learn about this with probability, an or translates mathematically to addition, all right? So I'd be looking at this and saying, for example, 2 plus negative 3. If I combine that with a positive 3, these would cancel out and leave you with just a 2. Right? That's what's happening here. They're opposite. It only works for the OR, but it's still, it's still something that you can kind of hang your hat on. Right? So this is law of disjunctive inference. All right. Now, the next part, I mean, I'm seeing a not S or R. So I look at that and say, well, the only other thing I see here that has an S or an R in it would be this statement right here. All right. So somehow using this R and that statement, S and R, then not R, somehow that's going to come together to give me a not S and R. All right. And so let me pull those aside. S and R, then not R. If I combine that with an R, see, this is one of those denies by denying kind of deals, right? Because my conclusion is refuted. Right? And again, no matter how complicated the expression looks, like it could be the most convoluted sentence in the world, but you could always look at it like, if I am an adult, then I can drive a car. Just forget about what it says. Once you see that sideways arrow, just think, if this, then that, and just talk yourself through it. If I am an adult, then I can drive a car. Well, guess what? I can't drive a car, so I must not be an adult. Or if I look at it with the perspective of a not, if I do the dishes, if I misbehave, then I do not get a reward. If I misbehave, then I do not get a reward. Because I wanted to get a not in there for the conclusion. So if I misbehave, then I will not get a reward. Then I tell you, you got the reward. Well, I must not have misbehaved. All right? So it allows us to draw the conclusion as the opposite of whatever the premise was. That's an example of modus tollens. It's not always simple, like P then Q, not Q then not P. Like you look at this and somehow you're related to that. It's not always the easiest thing in the world. It takes a little thinking. All right. Now the next one we talked about before. We actually talked about it with Venn diagrams, and we're talking about it again earlier in class. If you're negating an expression that involves an and or an or, you negate each part. All right. So the S gets negated. So S becomes not S. R becomes not R. And becomes or. So we flip everything. That's an example of De Morgan's laws. All right. And then that last one, which I neglected to put a line for. Well, I also neglected to make this a unique problem to begin with, so different story. So the last one, I need to somehow pull a not S from this. All right? So I'll just off on the side here. I have not S or not R. Well, I want to be able to cancel that not R so that I'm left with just an S. I can cancel the not R because I have an R here. All right, so if I put those together, I'll get a not S. All right, and that's disjunctive inference again. All right, I know it's complicated. It's not something, I'm not going to ask you to do this on a test, It's just you'll see in a little bit. I have a little assignment for you. It's a take-home assignment, so you'll have the opportunity to digest this stuff. I'm not in the business of finding the most complicated concept, teaching it to you, hoping for the best, and then testing you on it in the hopes that everybody fails. I mean, that doesn't make sense. All right. So I'm exposing you to the concepts so that you could start thinking logically. So that's going to make probability a whole lot easier. But, we're not just going to do it for the sake of doing it. Right? But it's kind of hard, like, if I don't bring up the laws at least a little bit and their proper names, then like, what am I pointing to? Like, this is a law, that's a law. What is it called? I don't know. So we use the proper names for the laws. As long as you develop the understanding of that's why that works, then things get easier. All right. I have a solved example on the next page, and I'll take you through one, as a group, but I put a solved example here so that you can see that a sentence that's this complicated could just be as simple as that. All right. So these two, by these laws, what I'm concluding here is that P or Q and not P and Q is really just the same as P. Now you can put the context in there. You can create, a scenario. I am washing the dishes, or I am eating dinner, and I am not washing the dishes and eating dinner. Like, you make a scenario. It's not always going to be easy to do. It's not always going to make sense, but it is doable. All right. So I wanted to show you how you can take, like I said, a complicated sentence here and show that it's equal to something very simple. All right. Because, I don't know how much experience people have with probability, but if I told you that you have two events, event A and event B, maybe event A is, getting a red card when you pull a card from the deck, and event B is rolling a 4 when you roll a die. The question could be, what is not A, the probability of not A and not B, or A or A? And if you can simplify that down to just a not Q, you've just made your life a whole lot easier. Right? Or in my analogy, it would be a not B. What I did here was I wrote the relevant rules, and also this wasn't here to begin with, so apologies again. I think it's the symbols that really throw me, because like the making of a note packet, that's not too bad, but like the double-sided arrows, I just neglect them for some reason. I don't know. So we want to be able to simplify this. Order of operations tells us to work within the parentheses initially. So that's what we should do. All right. So we have a P or P here. All right. So that, I call that, it's called the idempotent law, but I call that the common sense law. It's just, if you're not comfortable with the symbolism, then it's like nothing's common sense. But if I say I am wearing shoes or I am wearing shoes, you're like, so you're wearing shoes. Like, you only gave us the two choices, and the choices are the same. All right. It's like, you can do the homework assignment, or you could do the homework assignment. It's like, you're just confirming the disjunction. All right. So this is going to be equivalent to P, and that's because of the idempotent law, which says P or P is equivalent to P. All right. So I'm going to just rewrite everything else. Let me actually do that in red. So not P, and I'll leave the square bracket here. It really doesn't make a difference, though. From really any algebra class that you ever took, that a square bracket, we treat that the same as just ordinary parentheses. Right? Now this one, the not Q or P, that's a new one. Right? That's not law of disjunctive inference or anything like that. I mean, there's other ways to tackle this, but we do have a nice law that's kind of ready to rock and roll, and that is the implication identity, or the law of implication. That tells us that not P or Q is equivalent to P then Q. So what I want to do is I want to match this up with this and see what that'll give me in terms of an if then. All right? So first things first, it's in the wrong order. All right? So I can switch these two pieces around. Commutative property applies not just for addition and multiplication, but for ands and ors. So I can just swap these two. Actually, now that I'm thinking about it, we don't even need the implication identity. I was about to make that more challenging than it needed to be. Let me rewrite this again in a way that might be a little bit more familiar. All right, so this is the same as saying P or not Q and not P. All right. Now, we did this about 5 times on the previous page, but that doesn't mean that you're expected to have memorized everything already. You know, it's not the easiest thing in the world. But I will remind you what the law of disjunctive inference looks like. All right. So, like I said, this law would have worked, but it makes things more complicated. All right. So, if I say P and or Q and not P, the result would be equivalent to Q. That's the law of disjunctive inference. All right, the law of disjunctive inference. And what I mentioned earlier is that it's really just a canceling out. All right, so I have two opposites here in a disjunction in an or sentence. Those opposites are going to cancel each other out, and that's going to leave you with just a not Q. All right, so we're able to draw that conclusion, and as much as I tried to make it more complicated, the laws of logic stood in my way. All right. Just wanted to try to find a good breaking point. We'll do one more, then we'll take a break. Because I wanted to talk to you a little bit about the basics of probability. And to be fair, I am unfortunately without intent. I'm making probability sound like it's this dreadful thing that you should be terrified of. It's not. In its most basic form, probability can be very easy. It's the more intricate problems. Like if you have a spinner and it's got 5 equal areas on it and you spin, what's the probability of getting a 1? It's just going to be a 1 out of 5. I mean, that's not the hard part. It's being able to evaluate more complicated games, right? So what I want to be able to do is talk to you about carnival and casino games. And in order to do that, having a good sense of logical reasoning is going to be really important, right? So that's really what it's coming down to. I mean, because I'm imagining how I would be in this class as a student right now. Be like, is it going to get any easier? Or is this always going to be just complicated concept after complicated concept? I promise we're going to get there. sooner rather than later. All right? Not scare tactics. Although I do think I scared somebody away tonight. That was not my intention. No email. Let's see. All right, so again, I give the relevant laws so that it's easier to kind of decode what's happening, but it doesn't mean it's going to be easy. But the commutative law we talked about a little bit earlier, that allows us to swap some things around. All right, so we have, looking at this, kind of probably one of the more complicated expressions that we've seen so far. All right, but if we follow this absorption law, that's going to allow us to take care of this piece pretty easily. All right, but before I can do that, if you look at the structure of the absorption law, these two pieces have to match. All right, now if I'm following that model, I'll just pull the expression aside, not Q and R or not Q. All right, these two things do not match, but they will match if I swap the ordering here, which I can do by the commutative law. All right, so I'm going to rewrite this. I'll just do it up here. Not Q and not Q or R. All right. Now, if they do match, then we're essentially confirming the thing that matches. All right. So yeah, this is not Q and not Q or R. But if I follow this model here, if it has that same structure, then whatever the two pieces are that match, that's what our conclusion is going to be. So from this, using the absorption law, I can now conclude a simple Q. Sorry, not Q. And if I couple that with the P then Q, so P then Q and not Q, remember, talked about this on the previous page, that's the same as saying P then Q along with a not Q. All right, that's a modus tollens situation because the conclusion has been refuted. So the premise must be invalid. All right, so not P would be the result of this by modus tollens. And again, not as important that you know the name. It's the important thing that you can see P then Q, not Q, must be not P. And again, for a lot of them, you could just talk it out. There are some, the absorption law, for example, right off the bat, P and P or Q, therefore, as you know, as a conclusion, it's equivalent to P. Like, I don't know what sentence I would say that would make that make sense. All right, but if I get a 90 or above, then I get an A, I didn't get an A, must not have got a 90 or above. All right, that's modus tollens, as opposed to modus ponens, where we confirm the premise. If I get a 90 or above, then I get an A. I got a 90 or above. What should happen? You should get an A. All right. So it's, in a lot of ways, it's logic sense, but in a lot of ways, it's borderline common sense. All right? It's like how you would communicate with other people. If I give you money, then you give me the goods, right? Whether it's at the supermarket or at a restaurant, I gave you the money, you give me the items. Now it could go the other way around, like you're at a restaurant, you get the food first, then you make the payment, right? So I ordered something, right? I ordered a chicken sandwich. So I order the chicken sandwich, you deliver it. So if you bring me the chicken sandwich, then I give you money. Now, if I don't give you the money, in theory, it's because you didn't give me the chicken sandwich. But it's also a possibility that I just skipped out on the check. All right. Logic is very important, but not everybody adheres to it. All right. So let's take a little break, and then we'll discuss some elementary probability concepts, and then I'll give you the assignment. In terms of practical use, we get a lot out of probability, right? And we'll spend a good amount of time on this concept because there's so much we can do with it. Next class, I have probability games that we'll tackle together. One of which is a variation of the game of roulette, and another is a variation of craps. So I just call it different things, and I modify it to basically take the money element out of it, and just focus on the probabilities. But there is, it's tricky because you get into casino games. There's that natural gambling element, which isn't ideal, but there's so much good math in those kind of problems that it's worth investigating. And so I always use those games as a tool to teach the probability concepts, right? So you have the basic stuff like probability is a branch of math that deals with the chance of an event occurring. Right? Most people intuitively know probability equals chance, right? So what's the chances it's going to rain tomorrow? I mean, you might say, what's the probability it's going to rain tomorrow? But probably you're going to use the everyday language, like, what are the chances? But it essentially means the same thing. An event is a collection of outcomes of a procedure. Right? So if I'm looking at rolling a die, for example, or flipping a coin, I'll go with flipping a coin. An event might be getting heads, or it could be getting tails. Now, the sample space is the list of every possible outcome that you could have. All right? So for a coin, it's nice and simple. It's heads or tails, but those are the only possible outcomes you could have. All right? But then it begs the question, what if I flip a coin twice? What are my outcomes? So let's say, again, flip a coin twice. Your outcomes could be that maybe they're both heads. Could be that they're both, well, I'll say both tails, but I'll say heads then tails. Maybe it was tails then heads, or tails then tails. All right. I chose this particular order because this is the same as true and true, true and false, false and true, false and false. All right. So our initial setup for a truth table, the idea being that if you have two possible outcomes, you could define one of them as being the one that you want. We'll call that true. The other one would be the one that you don't want. We'll call that false. All right? So you could look at it the same way, but then it starts to get a little crazy when you want to flip a coin 3 times, 4 times, 10 times. Listing out those possible outcomes, it could be a nightmare. All right? So one of the things that we look for is kind of shortcuts through the maze. That's why we talked about the logic stuff, right? Because if we can clean up something that is complicated, maybe containing 3 variables, into something that only contains 2, then it's easier to go through the probabilities, all right? P stands for probability. A, B, and C are specific events. P parentheses A is P of A. That's how we read that, all right? So we read this as P of, that's an awful way of writing it. I'll just do it with a highlighter. It's P of A. All right. So you're really reading that as the probability of A. What is A? Well, it depends on the problem. All right. The next one would be P of not A. All right. So that not symbol is still going to be here for a while. All right. P of not A. All right. That's the notation because I want you to be able to say, all right, if I have P of H, I want you to be able to look at that and say, okay, that's a question, and that question is specifically what is the probability of getting heads when I flip a coin, all right? So then you would look at, like whatever the scenario is and draw that conclusion, but this would be probability of getting heads when you flip a coin. Now, H could mean anything, but in this context where you're flipping a coin, H means getting heads. I mean, it could be really anything that starts with the letter H. I mean, typically we define an event using the beginning of the alphabet, but we could also define it using whatever we want.
So the sample space would be the H's and the T's, or would it be the flip a coin twice?
This.
And then the flip a coin twice would be like that.
Say it again?
The flip a coin twice is like that.
Yeah. Yeah, this is the sample space for flipping a coin twice. All right. Now, I'm just reading it right off the page, but it is true. There are a few different ways that you could determine probabilities. One way is experimentation, right? And you may not, like when you see the example that I gave, you might think, okay, well, he's basically telling us not to use that because that's ridiculous. Like, I'm going to flip a coin. What's the probability of getting heads? I have no idea. Let me flip it 5,000 times and see what happens. All right. Yeah, you could do that, but I would never ask you to actually literally flip a coin that many times. We use technology. You could I could simulate flipping a coin 200 times very easily, right, using Excel. Right, and I'll show you how to do that as we get kind of moving in the right direction here. All right. And the idea when dealing with experimentation is that the probability should settle in with a higher number of trials to what it ought to be. So if I flip a coin, let's say, just suspend your disbelief for a second. If I say, what's the probability of getting heads when you flip a coin? And you have no idea. So you flip it 4 times just to see. And 3 out of the 4 times you get heads. Are you then going to say the probability of getting heads is 3 out of 4? Right? You only tried it 4 times, it's a small sample. Right? So maybe you try doing it 10 times and you get 8 out of 10 times being heads. You're not going to say 80% of the time when you flip a coin you're going to get heads. Right? Maybe you try it 20 times and you get 12, 30 times and you get 17, 100 times and you get 56. As you increase your number of trials, you're going to get closer and closer to the true probability because that's how nature works. It'll settle in on whatever the probability ought to be. All right. And actually, now that I kind of teased the whole Excel thing, let me just do that real quick. This is not the mouse for this device. Let me bring in, well, let's not bring up the roster. I'm just going to go to Excel. I'll use Google Sheets. It basically works the same way, but I prefer Google Sheets just because it's a little bit more mobile. Excel is too, but this one I never have trouble with. Right? So if I wanted to do, so we're going to flip a coin, let's say 10 times. All right, so flip a coin. And I want to do it 10 times. All right. So what I would do is let 0 equal heads, let 1 equal tails. You can go out, you can choose whatever 2 numbers you want, but if I flip a coin, let's say 10 times, I would use a random integer, a random function. On Google Sheets or Excel, it's rand between. It'll allow you to randomly select between 2 numbers. right? So rand between, and I want it to be 0 and 1. All right. This is not something I expect you to memorize right away, but we'll do some activities where we use Google Sheets or Excel. All right. Now, if you're not really familiar with spreadsheets, there is a learning curve, but it's not quite like learning the laws of logic, so it should be a little easier. All right. If I want to do this 10 times, I can grab this little boxy thing in the lower right-hand corner, which I believe is called a boxy thing. It's not. Drag it on down the line, and it'll repeat that computation for every cell that I highlight. All right. Now, the one thing about the random integer function is if I make any change to my spreadsheet, I'll just put in some dummy values here. It's going to change. You see how this is changing over here? Every time I make a change in the spreadsheet, it reruns the computation. All right. So just for the sake of not losing my mind here, I'm going to copy this and then do a edit paste special values only. All right, so now this could change all at once. This isn't changing. These are just the values. All right, so now I can go through and see the probability of heads is equal to, let's see, we have 1, 2, because I'm letting 0 be heads, 1, 2, 3, 4, 5, 6. So I'm saying 6 out of 10. All right, that's not the probability of getting heads when you flip a coin, unless it's an unfair coin. It should be 5 out of 10. It should be 1/2. One side is heads, one side is not. Now you have a 1 in 2 chance of getting the thing that you want. Now I'll just go kind of crazy with this. Let's say instead of 10 trials, I do, come on, trackpads. It's like the bane of my existence. Let me just get it so I can see the bottom here. I'll get rid of that dictionary thing in a sec. I don't know, like 500 trials, I guess. It's going to take me a while to count them all up, but, you know, it'll be fine. Show you a little trick. Okay, I guess I missed it. Try it out again using a technique that I like to call the right way. We're getting there. Yeah, almost there. There we go. Nice, nice set of values there. All right, but again, I don't want to change it on me. I got to disable this dictionary thing because I don't know anybody who actually uses it. Paste it here. I know on a Mac it's Command Option Shift V for the keyboard shortcut, but you just click on values only. I guess I didn't get it. Let me try it again. I'll do it over here. Edit, paste special, values only. Brings in all these numbers. And you could say, well, yeah, it's going to take forever and a day to count them all up. But I could use a count function to give me the values. Now, again, the purpose of this, the syntax for Python, Java, Excel, it all becomes a big blur in my mind. So anyway, the probability of getting heads, I got 267 zeros out of the 500. All right, so the probability of getting heads here, I'll just type it in the way I did before, would be equal to 267 out of 500, which isn't equivalent to 0.5. I'll show you. Equals 267 out of 500. That's about 0.534. All right. 6 out of 10 is 0.6. All right. So, yeah, the 0.534 isn't correct, but it's better than the 0.6 that we had. And if I did this 1,000 times, 10,000 times, it's going to get even closer to what it ought to be. All right? Because it is possible after 2 flips of a coin, you could think that there's a 100% chance that you're going to get heads when you flip a coin, because maybe both outcomes were heads. Right? That doesn't mean that that's the probability. Anyway, the whole reason I went on this little, I'll call it a tangent, but it's really with a purpose, is just so you can see that experimentation can be useful, right, when it comes to probabilities, because there are plenty of instances that can't be modeled by a formula, and there are other instances where even if you can model it by a formula, it's so complicated that you're like, you know what, let me just make a spreadsheet and see what comes up out of it. We'll work on I don't know if you're familiar with the Monty Hall problem, the let's make a deal. You got the 3 doors. Behind one of them is a beautiful sports car. The other 2 doors are goats. Personally, I'd rather have the goats, but those are considered the losing prizes. So the probabilities involved with that are pretty interesting, but it's not easily done with a formula. All right, so I'll show you how to experiment your way to that probability. All right, and when we talk about casino games, not easily done over the long haul with a formula, but if we create a probability simulation, we get an idea what's happening. All right, there is a formulaic approach, but for every problem, there's a different formula. Right, same general structure, but the formulas might be slightly different or massively different. Estimation pattern recognition. I made a little note here that that's the least frequently used one mathematically, right? In terms of finding raw probabilities. And when I say mathematically, to be fair, I mean in math class. All right? In the real world, estimation pattern recognition and simulation, experimentation, those are the more frequently used probability methods. Because if you think about it, you go to a casino, and most people, I don't know how much you know about roulette, but you might have heard, like, you always bet on red or always bet on black. There's the 3 colors. One of the colors is green, but there's only 2 outcomes associated with that. 18 are red, 18 are black. So if you're going to go up to a roulette table and say, drop $500, and you're going in and out, you're probably just going to say, okay, just put the 500 on red. And it's a 1-to-1 payout, so you win $500 if you win. Right? So you walk away with $1,000. Right? That being said, if I go to a roulette table and the last 10 times the wheel was spun, they all came out red, I'm thinking to myself, all right, that's a pattern. I don't know if that's a pattern I like. You could look at it and say, well, we got a nice streak of red, maybe one more red. Or maybe you could say, well, red's been coming up a lot. I think it's time for a black. I'm going to put my money down on black. Right? So based off of the pattern recognition, you would make a determination of what your strategy ought to be. Right? Roulette's a funny game because probability-wise, the different outcomes, they're massively different in terms of the probabilities. So if you bet on the number 7, and I'll show you the whole board and everything, but when you bet on the number 7, you have a 1 in 38 chance of getting that. But if you bet on black, you have an 18 out of 38 chance of getting that. So you would say, well, I'll just bet on black. Black, just betting on the color pays out 1-to-1. Right? Betting on the actual value pays out at, depending on the table, 35-to-1. Right? So if you bet $100 and you win, now it's a lower probability of it happening, but you walk away with $3,600 because $3,500 is what you get as the reward for winning, but you also get your bet back. Right? So you'd say, well, I'll just do that, but the probability is so much lower, and so it's not sustainable. Right? But as it turns out, there's this thing called expected value. Over time, assuming unlimited resources, which is a big assumption, in the long run, the expected value ends up being about the same, or exactly the same. All right, so I'll show you all this stuff related to that. And it's not a course on gambling. I got to be very clear about that. But if you have an understanding of a casino game, at least you could make smart decisions. right? So it's kind of like, I don't think you should do it, but if you find yourself in a position where you're going to do it, at least you're armed with the right information. All right. Probability rules. Oh, yeah, and weather. Probability associated with weather. How do you know that, or how do they know that there's a 30% chance of rain? I'm kind of not embarrassed, but I probably should have known this way earlier than I actually learned this. When they say that there's a 30% chance of rain, they're not saying that there's a 30% chance that it will rain. The rain's happening. It's just 30% chance that it's going to be where you are. Right? So, yeah, 2 years ago I learned that. Been teaching for like 25 years. But, not meteorology, so I guess it's okay. Anyway, probability values have to be between 0 and 1. Typically we go decimal, but you can go fraction as long as that fraction is basically not an improper fraction. It's got to be equivalent to a value that's between 0 and 1. All right. There's also complement rules. So, and it's kind of strange because the word complement, it means something different in different areas of math, but usually it means whatever's left. All right. So in the case of true false, the complement of true is whatever is not true, so whatever is false. Flipping a coin, probability of getting heads, that would be your event. The complement of that would be the probability of getting tails, right? Everything else. But then you come across situations like, let's say you're rolling a die. The event that you want to get the number 1. Everything else would be the complement. So that would be 2, 3, 4, 5, and 6. All right, collectively. I made up this example here. Given a multiple choice question with 5 choices, what's the probability of getting the correct answer just by guessing? If there's 5 choices and you're really just guessing, then you have a 1 in 5 chance of getting that. Incorrect would be the other 4. So 4 out of 5. If I take the probability of getting a correct answer and add to it the probability of getting an incorrect answer, the result should account, so the sum should account for all possible values, right? Because these two things, correct, incorrect, correct, not correct, right? P, not P, they're two exact opposites, right? So they should add up to equal 1. All right, 1 represents all possible outcomes. Or if you're looking at it in the sense of what does the number 1 mean probability-wise, it means that you have a 100% chance of getting this outcome. We call that certainty. All right, so just tying it back to logic, that would be the case when we made the truth table and we got valid. The last column was all true. That's 100% chance that you're going to get that outcome. All right, every possible outcome has been accounted for. And so if you think about it, if I answer a question on a test, I either got it right or I got it wrong, assuming it's multiple choice. All right. And assuming there's no partial credit, things like that. So that, it's a very simple problem, but it is something that we use to determine what's called significance. All right. So let's say I give a multiple choice test with 10 problems. And the probability of you getting, let's say, all 10 correct, I could tell you, but let's just say it's small. All right. It would be infinitesimal, teensy tiny. Then somebody walks in after having guessed on every single question and got them all right. I'm like, all right, you knew what the answers were. 'Cause you didn't guess. Because the chances of you getting them all right just by guessing is so remotely small that if you got them all right, then something else was going on. All right. That's like the student that walks out of a test. We all love this student. The one where the test was really hard, and that student is like, I totally bombed it. I didn't even study. And then the next class you find out that they got 100 on it, and you're like, well, you lied. Like, why did you say, oh, I didn't study at all? Yeah, you did. Otherwise, you wouldn't have gotten 100. Right? That's the I call it the miracle worker syndrome, where the person, it's not good enough that you get good grades. You have to make it seem like you put no effort into it in order to get good grades. Like it's a miracle. Or I'm just that smart. You know? So yeah, that's my little spiel on compliments. Rounding, we tend to go three significant digits, just for the the highest degree of accuracy. So I made the little note here. Usually means the thousands place, but not always. So it usually means 3 decimals. What we do is and really example 6 is the more important one. If you have a string of zeros after a decimal, you don't start counting the 3 decimal places until it transitions from a 0 to something else. All right. So you kind of ignore those first 4 zeros, then start counting. This is 1, 2, 3 decimal places. Then you cut it off here. All right. So that 9, like it's 5 or above, give it a shove. That 9 is going to make that 0 go up to a 1. All right. So it's a little bit of a twist on rounding, but it allows us to, instead of saying, well, it's 0. How do you know it's 0? Well, I went to round it to the nearest tenth, and that's what I got. We can get a little bit more significance out of it, a little bit more accuracy. And the reason is, like, why would we need to do that? You could have 2 very, very unlikely events, but we'd want to know which of these unlikely events is more likely. So you'd want to find the difference. Now, if you over-round it, you round it to the nearest tenth, you're going to say there's no difference, but when really there is. It just might not be a whole heck of a lot, but it might be meaningful information. The next page, I have sample space information. This is just reference, because we will talk about, coins. I didn't want to insult your intelligence, but I found nice images of coins, so I figured I'd put it in. Dice, I learned a long time ago that not everybody knows what the heck I'm talking about when I say a die. Die is singular for dice. Dice is plural of die. All right, 6-sided number cube. Most people are like, it when you see it, but I always assumed that everybody knew the term die, and I realized I was offending a lot of people. It's just a singular. All right, each dot represents a quantity, so the side that has a 1 dot is valued at 1, 2 dots is valued at 2, and so on. All right, and you have the cards. So in order of familiar to less familiar, going down the list, when I first started teaching, late 90s, early 2000s, most everybody knew the breakdown of a deck of cards. Now I find that in any class that I'm in, it's like the smallest percentage of individuals that are really familiar. Most people kind of know a little bit, but it's not really the way it used to be. All right, there are 4 suits. The suits are hearts, diamonds, clubs, and spades. All right, so you can see them here, but I'll tie it together real quick. These are the clubs. Diamonds and hearts, I think, are a little bit more obvious. All right, so diamonds, hearts, the ones that look like hearts. But then you have the spades. I find that when people get confused, they get confused between the clubs and the spades. Right? It's not every day that you're going to find a 3-leaf clover in your backyard, let alone a 4-leaf. But the spades, most people who are not as familiar with cards, they have trouble with those. And so I figured I'd label that for you. 13 cards per suit. So again, these are, we call it the suits. I have no idea why. It's been on my list of things to look up for the last, how old am I? Long time. But never did. Maybe I'll do it at some point. We'll see. But the suits are the clubs, diamonds, hearts, and spades. The cards that make up each suit are ace. So there's my ace. The 2 through 10, same deal. Not going to insult your intelligence. It's the ones that have 2, 3, 4, all the way up to 10. All right. The remaining ones we call picture cards or face cards. All right. I tend to call them face cards. You can go either way. You can call them picture cards or face cards. It's just, I don't know. It seems kind of weird, but I stay away from calling them picture cards because technically all the cards have pictures on them. Some are hearts, some are spades. So, to avoid confusion, I tend to just call them face cards, because there's a face right there. You see, in each of these 3 cards, there's a face. You know, we're not going to get into like the one-eyed jack and stuff like that. But, and by the way, in case you're wondering, one-eyed jack, he's got one visible eye. Let's just put it this way. I'm not going to ask you a probability question, and be like, what's the probability of getting a one-eyed jack, and have everybody be like, what the heck are you talking about, man? What's that? Why do they have the one-eyed jack? It's just, it gives an opportunity to bet, you know, because then you could say probability getting a jack versus the probability of getting a one-eyed jack. One-eyed jack is going to be less frequent, right? Only half of the jacks are one-eyed. So it's 2 out of 52. So the lower the probability, usually the bigger the payout associated with getting that as an outcome. Right? So, and then I have a list of prime numbers at the bottom. They come up in probability questions a lot. I don't really intend to ask you too much about prime numbers. I'll use a few examples, but it's not my intent to make things more complicated than they need to be when it comes to probability, although it may seem like that when we were talking about logic. But these concepts kind of tie together nicely. You have cards that have values from 2 to 10. And then, you know, you have some letter cards, A, J, Q, and K. But if I wanted to ask a question like, what's the probability of getting a card that has a heart on it and also a prime number, then it would help to know what prime numbers are. So just a refresher on the definition. Any number greater than 1 that is divisible by only 1 in itself. All right, so looking at this set of numbers, and you know, the number 2 is the only even prime number in existence. You'd look at each one of these values that I have listed. I went up to 43. And you could see that you're only going to be able to divide evenly into those numbers if you use the number 1 and you use the number itself. All right. So 2 is divisible by 1 and 2 because those are the only 2 numbers that when you do the division, you don't get a fraction. All right. We don't do anything with negatives because that opens a whole different can of worms. All right. So like 3 would be 1 and 3. 5 would be 1 and 5. Just because a number's odd doesn't mean it's prime. So an example of a number that's not prime but is odd is like 15. Because you could divide 15 by 1 and 15, sure, but also you could divide it by 3 and 5. All right, so it's not just the 2 values. So this is the lower numbers that are associated with primes. They have entire courses that deal with identifying prime numbers and different algorithms. This is not one of those courses. But we do want to have a little bit of understanding of what these things mean. All right. And the last thing I wanted to talk about was sample space size, because I mentioned it before, and you saw with the Excel demonstration that I did, that the number of outcomes that make up a sample could be could be astronomically large. All right. So how can I figure out how many elements make up a sample without actually having to count up the entire sample? So I use the count function in Google Sheets, but maybe there's a different way. And so I focus on two very simple cases. One is flipping a coin, and the other is rolling a die. All right, so for flipping a coin, there is a pattern that emerges, and if you go to the previous page, you flip a coin once, you got heads or tails. Those are two possible outcomes. Flip a coin twice, we had heads, tails, tails, heads, 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 in no particular order, tails, tails. We had four possible outcomes. All right, there is a doubling going on here. So if, and it gets a little lengthy, so I won't write it, but if I flipped a coin 3 times, you could have heads, 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 tails, heads, tails, heads, and so on, all the way to tails, tails, tails. There would be a total of 8 outcomes. Right? But you could see the pattern, again, pattern recognition, like I talked about a little while ago. We're doubling every step of the way, times 2, times 2. So the next one would be times 2. That'll give me to 16, yep. 32. But then it begs the question, well, what if I had some unknown number of trials? Like I flipped the coin 300 times, or I flipped the coin 20 times. It doesn't really make a difference. How can I get from here to my answer without having to know how many steps along the way I'd have to travel? Right? So we look at the relationship. To get a 2, we had 2 outcomes for a single flip of the coin. If I take that 2 and raise it to the first power, that'll give me a 2. 2 raised to the power of 2 will give me a 4. 2 raised to the power of 3 will give me an 8. So what we're getting at here is we have the number of outcomes per trial, and we raise that to the number of trials. All right, in next class, I'll get into the different circumstances in which we could use this process, but it helps us to, at least in these cases, come up with the total number of outcomes without having to double. All right, so 2 to the 5th, all the way up to 2 to the nth power. All right. And the value in knowing that is now we know the denominator of any probability, because numerator over denominator, part over whole, we now know the whole. How many elements make up the sample space? If I had a question like, all right, now out of these flips of a coin, what's the probability if I flip a coin 20 times that they're all heads? Now I have the ability to figure that out. But that's a different conversation for a different day. Same relationship holds true for a roll of a die. Number of outcomes per trial raised to the number of trials. All right, so the first one is 6 to the first power, 6 to the second. The 6 is coming from, that's the number of outcomes for any one roll of a die. And the power is coming from the number of rolls. So 6 to the third power, which would be 216. 6 to the, I put a 3 there, but it looks an awful lot like a 2, so let me fix that. 6 to the fourth power, which might be 1296. I don't know. Crunch the numbers. So 6 raised to the fourth power. Yeah, 1296. That's memory. You do the same problem over and over again. Some numbers tend to stick out. All right, and that'll happen with you all before too long. 6 to the fifth power. That one I had no chance. 7,776. And then, again, the number of outcomes per trial raised to the number of trials. All right. So is there a general formula that we could use? What is it? So we would say probability. Well, it's outcome, so we don't have to say probability. I tend to say K. K is a good value to use. K to the nth power, where K is the number of outcomes per trial. All right. If we were looking for a probability, then it would be kind of a different kind of problem. This just gives us the denominator. I want really random, so the likelihood that you're going to end up with the same puzzle as somebody else is kind of small. So the probability, if you will. All right. So it creates a puzzle, and it gives you a bunch of clues, and you might be familiar with this. I remember back in middle school, we did a lot of these. It's just I didn't realize just how useful these kind of problems are for getting you to think logically. Right? At that point, it was just a game. I remember you finish a test, you have nothing else to work on. Teacher's like, here, do a puzzle or something. That's kind of how it was. All right, so you can click on the story. It's up to you. I have never yet needed the story in order to understand what the question is. You could take notes. Same deal. If I'm going to take notes, I'm probably going to do it on separate paper. I'm not going to go here to not see the clues anymore, just type down some notes. That's not my thing. All right. But what we look at is, and in each one of these, there's a logical connective at work. All right. If you click on a clue, it'll go away. So don't click on it until you're done with the clue, until you're absolutely sure that you're done with the clue. All right. Don't click on hint. Don't click on clear errors. If you make a mistake, just start it over. All right. Because one of the conditions that you need to meet is that you get it 100% accurate. All right. You don't have to get the same puzzle. You could change puzzles if you want. All right. That's why I'm giving you a couple weeks to do it. All right. Because this might take a little while. All right. So we have reference to money, the name of the woodworker, and the type of wood. So, and this is the first time I'm seeing this problem. All right. So just to be clear about that. It says Irma's piece is either the $250 piece or the $275 item. All right. So for Irma, where's Irma? Irma's right here. It could be this one, $250, or the $275. I don't know which one it is, but if it's one of these two, it can't be the $300 and it can't be the $325. Right? Because if it's either the $250 or the $275, those are our restrictions. All right. I might still need this clue, so I'm going to hang on to it. Josephine's piece cost $25 more than the piece made out of ash. All right. So that every one of these puzzles is going to have a clue like this. One piece is more than the other. Like Tommy drove 500 miles more than Jimmy, like things like that. This is an important clue because it's telling me that Josephine's piece can't be the cheapest one because it's more than something else. So I can eliminate the cheapest price for Josephine. All right. Now it's got to be $25 or more, $25 more than the piece made of ash. Well, they're separated by $25 increments, so that's not really helpful. But since I know that the ash piece is not as expensive as Josephine's, then the ash one cannot be the most expensive one. All right, because Josephine's is $25 more than that, so the ash one can't be the most expensive one. It's got to be something less than the most expensive one. Then you have Gwen's item made out of ash. Right, so that's nice. For these kind of puzzles, I find it for everyone that I've tried, they give you a gimme. They give you one that's straight up. This is what it is. So Gwen's item is made out of ash. So click twice, it'll change it to a green circle. It'll X out everything else. All right. The item made of chestnut costs less than Gwen's piece. So Gwen's piece can't be the cheapest one. And the item made out of chestnut can't be the most expensive one, right? Because it costs less than something else. All right. So every go round with the clues kind of helps you zero in a little bit. The piece made of elm costs $25 less than Irma's piece. So the elm one, it can't be the most expensive one because it's less than something else. All right. So that can't be the case, which means rosewood must be the most expensive one, which X's out everything else in the rosewood column. But also, if Irma's piece costs more than something else, then it can't be the cheapest one. So that means Olivia's is the cheapest one. All right. Now, by putting in that last X here, I narrowed Irma down to being the $275 piece. All right. Now, if you can kind of cross-reference among the rows and columns, then that's good. But it might not be as obvious. All right. So if you don't see it just yet, then you cycle through the clues again. So Irma's piece is either 250 or the 275. Oh, well, we already got that figured out because we know Irma's is 275. All right. Josephine's piece costs $25 more than the piece made of ash. All right. So Josephine can only be 300 or 325. All right. So that limits what the ash could be. All right. So if Josephine, again, $25 more than the piece made out of ash, if Josephine is 300, then ash could be 275. If Josephine is 375, then ash could be 300. I'm sorry, 325. Then ash could be 300, which means that the ash cannot be $250. All right. Which also means, but it's already confirmed down here, that Olivia, since Olivia is at 250, Olivia can't be the ash, but we already knew that. All right. Gwen's item was made out of ash. We already got that accounted for. All right, so Gwen's item must be either 275 or 300. All right, the item made of chestnut costs less than Gwen's piece. All right, so the chestnut, the possibilities are, well, if I know Gwen is ash, and she's got to be 275 or 300. Then the item made out of chestnut can only be one of these two possibilities. So it can't be this one. All right, so you progress through, you cycle through, and see as you do that whether or not you can draw a conclusion. All right, the piece made of elm costs $25 less than Irma's piece. All right, so again, if it's less than something, then it can't be the most expensive one. So that doesn't look like it's helping unless we can, oh no, we have Irma right here, sorry. If Irma is 275 and elm is $25 less, that makes this one the elm, which makes Olivia's $250 item the chestnut. All right. Now, again, cycle through again, over and over again until you can kind of come up with it. So the item made of chestnut costs less than Gwen's piece. So I don't think we're there yet. Item made of chestnut costs less. Well, it's the least expensive one, so it must not be relevant. I think we're done with this one. Is either the 250 piece or the 275 item. So I'm going to X on that or click on it. Yeah, they put it down at the bottom anyway, so it's still going to be there. Josephine's piece costs $25 more than the piece made of ash. So Josephine, I don't think we have any help there yet. Because if it's this, then Josephine can be here. If it's this, then Josephine could be there. So that's not helpful. Gwen's item was made of ash. No help there. Well, Gwen's item can only be this. Yeah, so no help there, so I get rid of that. It's less than Irma's piece. Piece made of elm costs less than. Man. I feel like I screwed this up. That's frustrating. The piece made of elm costs $25 less than Irma's piece. I think I put that in as chestnut. I got it backwards. Dang it. Should be that. Clicked on the wrong thing. So that has to be true, that has to be true. And then everything falls into place. You know, that's the unfortunate thing, because if I were in your position, I'd have to start this whole thing over again. All right, so, well, anyway, just to finish it up, 300 corresponds with Ash. Ash corresponds with Gwen, so 300 corresponds with Gwen. Only leaves one remaining possibility over here. Once you're in the end game, you'll see a pop up here, and it'll bring you to answers, because it knows that you don't need the clues anymore in order to continue the process. So now it's just comparison. So 250 Olivia Elm. So Olivia Elm. Irma 275 Chestnut. So Irma Chestnut. And then there it is. All because I read something incorrectly. What can you do? Do it right, I guess. Congratulations, you solved the puzzle correctly. Stand by for results. What I need from you is this. All right? So it'll say, oh, you know what? I corrected my mistake so I didn't get a penalty. Look at that. That's nice. So what you'll do is you'll screen grab this. All right? As long as it says no penalties up here, then you're fine. All right? Don't worry about the elapsed time. Don't worry about the total score. I could lie to you and tell you that the only reason it took 655 seconds is because I was instructing and giving all the explanations along with it. But I can tell you that I'm usually living in the very slow, slow to very slow area. All right? I take my time with this kind of thing. So I'm not looking for you to set a record. All right? So, yeah. So that's the puzzle. I'll go over another one next class.